Welcome to the week 7 of Fundamentals of Additive Manufacturing. So, today we will be discussing about the FDM process, and we will mostly discuss about the nozzle head which we use in our FDM printer, and we will try to correlate it with the assignment questions that you have related to the nozzle head, and like how this nozzle head looks. We will correlate with one of the model of the nozzle head. What are the components that are available, uh, like the filaments, and we will be discussing on the component stepper motor, drive block, everything. So let's start. After that, we'll also discuss some questions. Okay. So this is overall assembly of a FDM printing head, where you can see a drive block, gear, mount, heated liquefier, nozzle, stepper motor, filament, and your thermal tube. So like sometimes it is of PTFE, or we can also say it as Teflon. And on the right side, you can see the feeding mechanism, how this entire these gears mesh. This is a model, and this is a real picture where you can see the heater mount and the roller, how they're meshing through. Here we give the feed. What happens is we okay, I'll just start from the beginning. Just let me change this color. Yeah, my recording had stopped, so I restarted it. So, so if you're working in a process something like FDM, so you have to understand that the problem will be always there, and you have to understand this working principle. Like I have a gear here, there is a idle roller. So when the filament will come from, it will break at this point. Uh, or sometimes when this compression is increased for some limit, at that time it may also break, and a bulging may be created. So here I have a filament, and there is a gap in between. So filament, and if there is a, suppose I have a filament and there is a gap in between, so the filament can't go inside or outside. So what you have to do is open this cover, and you have to manually remove the filler from the top and bottom. Then only uh, it will start to print. But the main problem in the FDM printer is whoever is using it, that you have to really understand the mechanism of mm, working principle of this entire feeding mechanism, how the, so that whenever, because the FDM printers have a usual habit of clogging. So, and the frequency of clogging is way too often. So to reduce all this, to tackle with all these problems, you need to understand how exactly the principle works. Like sometimes the clogging may have occurred uh, in this nozzle area inside the Teflon tube. Sometimes the Teflon tube may not be, it would have, its diameter would have reduced, or it would have melted, which would not allow the filament to easily pass through it. Sometimes there will be some unwanted particles in this gear rollers. You need to reduce those small minute polymer particles. Sometimes what will be happening is that your uh, extruders, which will have heaters, those won't be working. Those won't be creating the stable temperature for working. So these are some specific problems. uh, Sometimes your gears may not be meshing properly. sometimes there won't be enough feed, sufficient feed, so that filament will go inside this uh, pinch roller mechanism of gears and get through to the nozzle. So sufficient amount of problems has there are sufficient number of problems which we need to tackle. So here we see this exploded view. Now in this exploded view, what are the different components in the nozzle head? The first thing is where we have a stepper motor. So let's start with the stepper motor. So in FDM printers, minimum 4 stepper motors are there. Okay. Now, if you have a 2 nozzle head, then it is 4. So one is for x-axis, y-axis, z-axis, and one is for filament. X-axis, y-axis, z-axis, and one is for filament. Okay. So and the cost of this stepper motor for a commercial level printer is between 500 to 2000. It depends on, and the RPM with which it can be rotated is limited to 100 RPM, because higher RPM is not required in the 3D printer. So actually uh, uh, this stepper motor can go up to, but these stepper motors here in, it is only required mostly 100 rpm, but actually these stepper motors can go up to 1000 rpm, but it is not required. So most commonly uh, we have a torque of some 1.2 newton centimeter. It costs around uh, between some 66,500 to 6,000, 2,000, 3,000. Now, if you buy a printer of up to 2 lakhs, and if you buy a FDM printer of 2 lakhs, so the motor will be there. And uh, whatever I am talking, it depends on varies according to the cost of a 3D printer. So we have 3D printers of FDM which start from 10,000 rupees and which goes up to uh, maybe 60 to 70,000 million if you want the industrial grade. And you can also, so that is what it varies. Okay, so this comes in the range of so whatever we are talking, this comes mostly in the range of 60,000, 2,000, 70,000 till 3 lakhs. Now, these range of printers, they mostly go till like 60, 70,000 printers, they go mostly till 60 to 50 degrees Celsius. Some go till 350 degrees Celsius. So, if you're trying to use a composite filament for those type of filament, you require a very high temperature. A very high temperature means at least more than 250 to 60 degrees Celsius. Because like when you have some composite reinforced filament, like pipe, suppose you have glass reinforced filament, or you have carbon reinforced filament, so these will require mostly high temperature. Suppose it is a combination of glass ABS, carbon ABS. ABS is a polymer. So these require high temperature. But same if this glass and carbon are combined with PLA, it will work within 240 degrees Celsius. But these require more than 240 degrees Celsius mostly. So now also that if you try to print the same filament of which require high temperature at low temperature, the quality sometimes it will get printed, but it won't be of the desired quality which you are requiring, because there won't be the proper fusion between the two layers. And other thing is that we have some sometimes these nozzles uh, may face a lot of wear and tear if you uh, go beyond its required temperature. It may work, but it will keep on wearing and tearing easily. Now, okay, just give me a second. I'll just open one more slide. Okay. So in this nozzle, the polymer melt is under stress. Now, there is a part of deformation energy being stored elastically. When the polymer melt is no longer constrained by the walls of the liquefier, the stresses that were acting on the melt in the nozzle are relaxed, leading to radial expansion of the melt, and here we have this phenomena die swelling which occurs. So die swelling is the ratio of maximum diameter of the extruded material to the diameter of the die opening, referred to as the swelling ratio. Now, in some small scale printers, these feedstocks are a loose coil. Okay, feedstocks. There is a feedstock behind this filament. So in small printers, the feedstock is a loose coil, while in some larger manufacturing system, these feedstock is coiled inside a cartridge to supply the system. So in both cases, the filament is pushed through the system using a pinch roller mechanism. Pinch roller mechanism is somewhat. So these are the rollers. Here we put the filament feedstock and these this passes through a heated liquefier and this gets compressed. Suppose if this is this much thick, now this gets compressed. This is the nozzle. and this is your final build material. Now these are known as the feed pinch rollers. Now in either case the filament is pushed through the system using a pinch these roller mechanism. Now stepper motor is connected to one of the rollers providing energy to move the filament through the system. Typical roller materials are, we can say, polyurethane. Now these one of these rollers, as we discussed, these have a grooved or toothed surface like this small tooth surface like a gear to create sufficient friction for the roller to grab the filament and feed it to the heated liquefier without slippage. Now the pressure on the filament between the rollers is typically sufficient to slightly deform the filament, usually leaving very small tooth marks, but these should be designed so as to avoid crushing the filament. That is, there should be sufficient force so as to push the filament through these rollers into the liquefier, but it should not crush the filament. So a pinch roller mechanism is used to supply material to the liquefier in FDM like processes. Now filament feedstock is in tension above these rollers, which pulls the filament from its source. Here it is in tension. Now below the rollers, these filaments, these are in compression. So here the feedstock, these are in tension. Here below it is in compression. And this is further pushed against the constricted opening of this print nozzle. As I said, this opening of the print nozzle is constricted. So obviously here there is your this viscoelastic mechanism going on, which helps the filament to reduce from a, we can consider from a dia in case of FBM 1.75 m to 0.3 or 0.4 mm. So this is the basic working principle of a FDM principle. Now sometimes what happens, and the most common failure of the FDM process is when this is your rollers, this is your the nozzle feedstock filament comes through this and it breaks. This is the most common failure of FDM process. Now this is the critical force which we relate to our buckling loads. Now when this compression reaches a critical limit, the feedstock filament can buckle. The feedstock filament can buckle when the compression reaches a critical limit. Now why this happens? The compression on the liquefier, here the liquefier which is there, the compression on the liquefier side of the feed rollers places a limit on the Q. Q is the volumetric flow rate. Q, volumetric flow rate, it is a product of transfer speed, width and your layer thickness. So what happens is, the compression on the liquefier side of the feed rollers places a limit on the Q, and when this happens, the compression reaches the critical limit and feedstock filament can buckle. This is one of the most common failures of FDM process. Okay, moving on to our previous discussion. Now we will again go back to our exploded view. Okay, so we will go back to our filament, spring, gear, roller, lever, bar mount, heater, nozzle. These all things you can see. Now there is a PTFE entrance guide, which is, I think, figure, yes, yeah. So here in this we have a PTFE entrance guide. Now there are two guides. One is on the top and other one is in the bottom at your printer. See here, there are two guides. Okay. So in most of the printers only the bottom one is there, the top one is not there. Okay. So because at the top there is no heat, so you don't need any PTFE guide because this is temperature resistant. So even it is 50 to 60 degrees Celsius, but here temperature is high, so you need a insulation. So for this purpose we have this Teflon. Okay. If you know, like we have PTFE. PTFE is poly tetra fluoroethylene. PTFE. So it has a melting point of 320 degrees Celsius, and I told you that your printers, the printers in FDM have can go till this range. So it can protect, insulate and protect the external component. So this is the functionality of a PTFE tool tube. Now the other thing which we have here is the, okay, and also, like you know very well that Teflon we use in utensils like frying pan, etc. So you can relate now. Okay, so next is we have a driver roller. In some, like I said, in some printers it is a form of gear which is in the form of tooth, and in some uh, other printers we may have some kind of we have a group, it's mostly made of rubber or polyurethane, also known as TPU. So we are using rubber and polyurethane because this type of material has high wear resistance. Now comes the question, so for ideal roller, how much function should be there so that one friction factor is 1 kf? So this also we will come and discuss about this later. So we denote it by kf, friction factor. So this question we'll discuss, I think it's here. So in the pinch roller mechanism, what will happen if the friction factor is less than 1? One, filament is crushed by the rollers, filament slips between the rollers, or uh, ideal gripping and feeding between the rollers and the filament. Now, Kf friction factor between the rollers and filament. Now the formula for the feed here, which we discussed, this is the formula for the feed rate. Now feed flow rate, that is the feed flow rate. Now we are discussing about the feed rate. Vf is the filament feed rate, Q is the flow rate, df is the diameter. Okay, so Vf is equal to Kf into 4Q by pi d square F. Now F is the feed. Now when the filament is crushed by the rollers, this Kf is greater than 1. When filament slips between the rollers, Kf is less than 1. And when Kf is equal to 1, there is ideal gripping between the rollers. And practically you can also test this by changing the dia of your filament. Okay, so I'll just tell you on a personal experience that the filament dia filament feedstock dia, this should be between 1.7 to 1.8 mm. This is the range, but the filaments we put there are in this, are having the diameter of 1.7. So once when we decrease this to, we had this filament, we made a filament of approximately 1.65 mm. So what happened is there was no gripping between the rollers. So we just pushed the filament, and since it could not grip, it came back. Okay. Now once more, when we put this filament of a thicker dia, like beyond 1.8, so um, we forcibly pushed it. Okay, the filament got gripped, but thing is, what happened, it got stuck, it did not print, clogging occurred. So both ways you will face either some problem. Filament was not able to be mounted between the rollers. So when your friction factor is 1, then only there is ideal gripping and feeding between the rollers and the filament. Okay, we'll again go back to a previous discussion. Now, usually also we see that after 1 or 2 years, our K value, it starts to decrease. Now, what happened after 1 or 2 years? Why the K value starts decrease when it already has ideal friction factor? What will happen during the printing process? It will try to slip so that your filament will not be dispensed from the nozzle. So ultimately, there will be porosity in your component, which will and you will always try to eliminate the porosity in your component for a better, uh, for an ideal specimen or ideal sample. So what you can do is, we can change our roller, which is very cheap, some 200 to 5, it will come between 200 to 500 rupees, and we can easily do it by ourselves itself. So what will happen is, now one more concept is, what will happen if we increase the speed in this. Now here, if we increase this speed, when Vf increases, what will happen is, if we take it as the buckling, which we already discussed. So The buckling will, this will vary. This will always occur. Okay. So these were some of the basic things about how to mount, how to control the friction factor, about the importance of PTFE, about your heated liquefier, stepper motor, and various other things. So also one thing is, the more apart from all these things, how you slice using some slicing tool. These are mostly open source softwares like Ultimaker, Cura, Flash Print. These are the most common which we use in India. Also, each printer, they have made some specific software for their printers. They can also tag along with those softwares. So, how you give the slicing, whether it is your printing speed, the more print, the more slowly you print, your sample will be printed better. But again, increasing the print speed will also, decreasing the print speed will sufficiently increase your time. There is a print speed, your various other joining or adhesion things like raft, brim. When you print dual material, like one nozzle having one material, another nozzle having another material, then you are always suggested by the printer to add walls, so that if there is some uh, oozing out of extra material from the nozzle, that will be wiped off by this wall. Okay, then how much is your retraction speed, how much is your print speed, whether you have kept the fan on or not. So for printing some uh, complicated structures, we need to take care of all these things. And whether you are giving a raft, brim, support structures, walls, also whether you have adjusted the temperature as per the material temperature, leveling of the bed before printing. So these are some of the very crucial factors for getting an ideal printed sample. Okay, so let's now start with the questions. Now, which of the following is the correct process for FDM process? The correct one is creation of CAD model, slicing, area filling, deposition of buffer layers. Now, the process steps are creation of CAD model, converting to STL file, orientation of STL file. If this is your bed, print bed, and this is your X, Y and Z. So whether you, and if this is your sample, so whether you want to print, this is your sample, so whether you want to print the sample this, or whether you want to print it like this. Okay, this is along X axis. Now if you rotate, whether you want to print the sample vertically or at an angle of 45-degree by giving support. This all again matters how you want to get the sample printed. Now orientation of STL file, then generation of support. And suppose if you're making, like I'll say you example, if you're making a tensile sample and you will be loading it along this, so it is always better that your printing direction is perpendicular to your loading direction. Generation of support, slicing, then is area filling, then generation of the G codes, then deposition of buffer layer, deposition of main support material, then your removal of the support after your printing is over, and surface finish. Next is, we already discussed this question. Next is staircase effect is visible in which of the following processes and why? Okay, this is pretty simple. Staircase effect is in use deposition modeling. Now, staircase effect this is not visible in SDM process. This is shape deposition manufacturing. Why? Because this does not use conventional slicing. And why this happens? Here in this process, we match it with the original geometry. Whereas in FDM slicing, we makes use of visibility concepts. And that is why here, since segmenting occurs, the part is free from staircase effect. Now, okay, this thing we were discussing, we left in between. When polymer melts, leading to radial expansion of the melt, the process is called as die swelling. Okay, so this is the build material melt. It comes through this and swells. This is D2, this is D3, and this swelling ratio is D3 by D2. Okay, so now the next question. In FDM process, the bead area varies according to which of the following? Now, the correct answer is Weber's numbers and Reynolds number. Okay, so we'll discuss little bit on this. Now, suppose this is your build area. Consider this as the region 1 and this as the region 2. Now, consider this as the H and nozzle prints, and you get the product, final product. Now, your critical velocity is pi square d2 by 2 4 delta p by 8 eta L2 h square. Now, this area is a function of q by Vt. Q is the flow rate, and this is velocity of print head. Now, AB minimum, your minimum area of the bead is h square by pi, and this is your h, which we were talking about. Now, this bead area, this varies according to this h, which is a function of both Weber's number and Reynolds number. So I hope it is clear. Now, the one thing I want to mention again in the last question about the die swelling. Now, like I said, here the polymer melt is under stress, with part of the deformation energy being stored elastically. When the polymer melt is no longer constrained by the walls of this liquefier that were acting on the melt in the nozzle, this is relaxed and the elastically stored energy is released. This leads to a radial expansion of the melt, referred to as die swelling. Okay, this is the radial expansion of the melt when the elastic stored energy is released. Now, the value of this swelling ratio, it depends on the material properties and the geometry of the extrusion nozzle. Okay. And also there is a remedy for this. Some fillers like ceramic particles or carbon fibers tend to reduce this die swelling. Now, regarding this critical velocity, so when the liquid properties are not directly involved in the stability limit presented given in this equation, the impact of exceeding the stability limit and the ability of a material to neck down from AB to AB minimum varies based on the Weber's number and Reynolds number of the liquid. Okay. Next question. How is the cross-sectional area of the bead related to the velocity of the print head in the FDM process? Now, AB is equal to Q by Vt. You know that flow rate, and this is the velocity of the print head. This is the cross-sectional area of the bead and volumetric flow rate. Now, we know AB is equal to pi d2 by 2 4 delta P by 8 eta L2 Vt. Now, the velocity, now suppose now suppose the velocity varies at the start and stop of the each successive layer, as well as when there are sharp turns in the tool path. So, suppose this is your okay. Now, velocity is not in constant at the beginning and at the end. So, in other words, velocity varies at the start and the stop of each successive layer. So, most machines adjust the filament feed rate to compensate for this. However, any degree of lag in the control feed rate controller will respond in a corresponding degree of under or over deposition, which we will now segregate here. Okay, this is the Q, this is the V velocity. So this is the start. Here under deposition occurs. Print head is now accelerating. Here there is normal deposition, and here there is lower deposition. Sorry, over deposition. Now here the print head is de-accelerating. Here there is the steady print head, and here it is the print head is increasing. Now this is the extruded road. This way the extrusion occurs. So one can always adjust Q with Vt by changing the filament speed appropriately. Okay. So the correct option for this question is the cross section area of the bead will be inversely proportional to the velocity of the print head. Now, okay, this is a plain straight question. In a FDM process, the cooling process of a single filament follows which transfer model? One dimensional steady state, one dimensional transient. Transient, it is one dimensional transient heat transfer because we are changing from one mode to other. And this question we just discussed, how the use of ceramic particles or carbon fibers tend to reduce which effect? It affects the effect of dye swelling. Okay, little bit I'll discuss more on this question. Now, why we are saying it as a one-dimensional transient heat transfer? Because we here have conduction as well as convection. Now, suppose this cooling process of a filament, this is simplified into a 1D transient heat transfer. Now, this already the previous little deposition rod which I wrote, which I modeled, it is considered as a, consider this as a one-dimensional block. Okay, this as a one-dimensional block. Now the head moves at a constant speed of v along when the x-axis, along the x-axis when extruded. The origin of the reference coordinate is set as the extrusion head. Now because the mass of the foundation is much higher than that of the filament, so conduction at the interface would not change the temperature of the foundation. So the conduction heat transfer with the foundation can be considered in the form of convection. So that is why it is one-dimensional transient heat transfer. Okay, so these were all the questions. Okay, so any doubts?